Okay, well, good afternoon and welcome to another in the series of SETI Talks, our weekly colloquium. And I can say good afternoon because it is, in fact, afternoon at this point. I want to say that I'd like to welcome everybody to the last colloquium talk at this venue. And I want to hasten to say it is by no means the last SETI talk. So I know there had been some concerns that because we are losing this space, we are going to be stopping the talks. That is not the case. I don't know whether it was Richard Nixon or Barnum and Bailey who said the show must go on, but the show will go on. Actually, Barnum and Bailey is closing down, which is so it's not really a good comparison. But we will be continuing these talks. We have actually serious discussions going on with Google. Google has agreed to host talks, but initially for internal consumption for Google employees. And we're trying to see if there's a venue there. They have some where there's the right kind of access that would allow public participation as well, open to the general public. Those would likely be then in the evening. We're also in close communications with Facebook and with Lockheed, as well as University of Santa Clara. So I suspect that within the next couple of weeks, we'll have a venue nailed down, so we will have a talk in April. We will not have a talk next week because we don't have the venue, but I do believe that we already have that talk scheduled. We've just postponed that next talk into an undetermined date in April. But we will be continuing the series. We will be continuing to do what we've always done, which is record them on YouTube. They're available on our YouTube channel at SETI Talks. And we have over 400 of these lectures on that site. So if you haven't availed yourself of that library of information, please do. It's quite impressive series of talks. I'd also like to, especially since this is the last time in the Microsoft facility here, and by the way, for those of you who haven't been with us in the last few weeks when we've been talking about this, we have been very fortunate to be at this really wonderful facility at Microsoft for the past year or so. And inexplicably, Microsoft is tearing this down because, as you can see, it's pretty shabby and run down looking. And so they're going to be building a whole new campus. And as a result, we have to go find a different home. But we do appreciate their support. And I'd like to actually have a call out to Felix, who's in the back, and his team. If people could just give a nice hand to Felix, because Felix and Tim and the rest of the team here at Microsoft have just done an outstanding job helping us out. They've been so cooperative and supportive in helping us get our films made and getting them up on site and all the audiovisual support. So really big appreciation for Felix and his team, and again to Microsoft. So the other thing I'd like to do, because this is an Exoplanet talk, and these are always among my favorite topics here, is have Bill Barucki stand up and say hello again, since he's, after all, the father of the Kepler mission at NASA. So it's always great to have Bill here. I think I just saw Russ Belikov coming in as well from Ames. And my own son Michael is here from Google, so a call out to Michael as well. So anyway, thank you again for coming. We will use the email distribution list as well as our website as well as our social media to give you information about the next talk, its location. We are trying to work in this general area so that we're close to Ames, close to the Institute, and I think there's something symbolic about that. But all right, so we'll get everybody informed. Please, check our website and follow us on our Facebook and Twitter and Google Plus accounts, and stay tuned. But we'll get the word out as to the new venue, location, date, and time as soon as possible. And with that, I'd like to turn the mic over to my colleague Matt Tiscarino, planetary scientist at the SETI Institute, to introduce today's speaker. Matt.
All right, thank you, Bill. Good afternoon, and thank you for coming to today's SETI talk. Our speaker today is Ian Crossfield. Ian started out as an engineer at JPL and then decided that rather than building and flying telescopes, he wanted to use them to do science. So he went back to school and got his PhD from UCLA and has now continued on as an exoplanets researcher. Now he works at the University of California at Santa Cruz, just over the hill on the coast. So today he is here to talk to us about Kepler's rebirth, science with K2. So let's welcome Ian Crossfield.
Thanks for that introduction, Matt, and thanks to everyone for coming out today on what I guess is our last SETI talk here in this venue. So it's an honor to be here to talk to you all about this, especially in such august company. So hopefully we can have some fun for the next hour talking to you about the research I and my team have been doing using the Kepler spacecraft and its repurposed, sort of reborn mission, which we call K2, to do a lot of really interesting and exciting exoplanet science. And I don't know how interactive these things are. If you have questions, if something is not clear in the middle, feel free to shout it out, or you can just wait until the end, however it suits you. So I should just say also that this work is supported by grants from NASA, even the National Geographic Society, who supports field work. They count that as just going to the telescope on top of mountains. So they gave us some funding for that, and the NSF as well. So we're certainly grateful for all of that support. So the background graphic here, just sort of to set the stage, is to really remind you that I'm a real observer of exoplanets. So I don't do so much of the theoretical or modeling work that underpins a lot of this work, but I really like and enjoy using my big telescopes. So this shows most of the telescopes I'll mention, plus a few that are coming up in the future that aren't even around yet. But we'll spend most of the time talking about the Kepler mission, which is actually the smallest one here in the diagram. This is from one of our early press releases from the K2 mission about a year ago. Each of these little dots were one planetary system that we discovered in each of these K2 fields across the sky, and I'll talk about exactly what that all means. Down here below, the biggest one here is actually something that's really exciting coming along in just the next year. This is called the TESS mission, which will do what Kepler and K2 did for small patches of the sky, but TESS will do it. We'll look for new planets all across the sky, so basically everywhere that you can look. So TESS is going to be a really exciting mission that we're all looking forward to as well. And then you might recognize things like the Hubble Space Telescope, which we're using to characterize the atmospheres of these planets. The James Webb Space Telescope is sort of the super Hubble that's coming along also in about a year and a half. It's really going to be a superlative facility for studying the atmospheres of these planets. And then big ground-based telescopes and other space telescopes coming along in the future that are also going to let us study all of these planets and find new planets in exciting ways. So we really need all of these observational resources. So if you just remember a few key things at the end of this talk now, here's what they should be. So first, I'll just sort of briefly give you an introduction on how we find and discover and characterize some of these planets, and how especially the K2 mission has really given new life to the Kepler mission, which was worried for a time might have come to a premature end. I'll talk about the work we do confirming these planets and how we need lots of additional observations from ground-based telescopes. I'll talk a little bit about the legwork that actually goes in, but I'll spend more time, I think, talking to you about the third point here, which is that we're finding hundreds of new planets using the K2 mission in this sort of second life of Kepler. And then finally, I'll talk a little bit about some of the exciting work that still lies ahead in terms of exploring exoplanets and finding new systems like that. So let's set the stage. So this is a blank canvas here showing the size of a planet. I'm going to plot planet sizes here on the vertical axis relative to the size of Jupiter, and the length of a planet's year, so how long a year is on this horizontal axis. So if we plot the solar system planets down here, you can see that they really only sort of fall to the right, in the rightmost area of this plot. That seems sort of strange that I've left all of this blank area off to the left here. But that's because what the Kepler mission really showed us unambiguously for the first time is that there are thousands of planets, and most of them, or many of them, have orbital periods much shorter than those of the solar system planets, even though many of them are much larger than the planets in our inner solar system. So there are thousands of planets sort of the comparable to the size of Earth or Uranus and Neptune, all interior to Mercury's orbit around our own sun. And so in addition, there are lots of giant, very short period planets. We call these hot Jupiters because they're the size of Jupiter, but they're only orbiting they only take a couple days to orbit their star, so they're very close in. And we also see sort of planets that are giant planets on long period orbits like Jupiter itself. And the fact that there are all these planets out there really shows that our solar system is not, as we might have predicted 10 or 20 years ago, is not the typical sort of end product of the process of planet formation. That solar systems like ours may not be infrequent, but it's certainly not the case that every system looks like our own. And it's also the case that there aren't many black dots here. Each of these represents a known exoplanet, just because they're really tough to find on long period orbits and at very small sizes. So it's not empty because there are no planets like our own. It's just we haven't quite been able to find very many of them yet. That's actually one of the original goals of the Kepler mission, which I think it's been pretty successful at. So most of these planets were discovered using two different techniques. And maybe some of you have heard of some of these before. The first technique that was really productive in finding new planets is called the radial velocity technique, or the Doppler shift technique. And it relies on the fact that as a planet and its star orbit their common center of mass, the planet is actually really dark. This is just a movie, obviously, so we can't see the planet itself. We only see the very bright star. And as the planet and star orbit this common center of mass, the light from the star is Doppler shifted back and forth, and we can use spectrographs on things like the automated planet finder up at Lick Observatory, just up the road an hour or two, or at Keck Observatory out in Hawaii. We can use spectrographs on those to measure that Doppler shift and measure both the orbital period and the masses of these planets without ever actually seeing the planet directly. So an even more productive technique, and the one that the Kepler and now the K2 mission use, is called the transit. It's called the transit technique. And this relies on the fact that when a planet crosses in front of a star, as this movie is not showing, the brightness of the planet decreases as the planet crosses in front of it. And if it's a small planet, you get a shallow dip. And if it's a big planet, you get a deeper dip. And so from the amount of light that's blocked by the planet crossing in front of the star, you can actually infer RP, the radius of the planet, relative to the size of the star. We've been studying stars, astronomers have, for over 100 years, so we understand stellar radii pretty well. So we observe the transit depth, and we can measure how big the planet is. And if we see dips occurring every 38.6 days, we know that that's the year of that planet. That's how long it takes it to orbit the star. So that's the transit method. So the transit method tells us the size. The radial velocity method tells us the mass. And so if we can measure both of these quantities for particular planets, we can actually start to learn something about what's the sort of bulk composition that a planet is made of. So we can plot here now each of these different points are different exoplanets with radii measured from transits and masses usually measured from radial velocities. And you can see, and these curves here show curves of different sort of model planet composition. So this brown curve here is a rock-iron mix, just like we think Earth and Venus are made out of. And you can see there are a number of planets, exoplanets, with measured properties who lie right along this line. And presumably these are rock-iron planets of a bulk composition similar to our Earth. Whether they have water or an atmosphere or life, we don't know at all, but we know at least in a bulk sense they're similar to the rocky planets in our own solar system. We see that there are some planets that may be denser than these, and we see a lot of other planets that are much larger for a given mass, so they must be much lower density. Even if you had a sort of toy model planet that was made entirely of water, which is a very common, relatively rarefied substance, you couldn't have a planet this big, so they have to have a big complement of hydrogen and helium gas. So all of these things must be sort of mini gas giants, sort of smaller, scaled-down versions of Uranus or Neptune, which have a lot of gas in them. So just by measuring the mass and radius from radial velocities and transits, like a mission like Kepler, we can start to say something about what the planets might be made of. So that's one of the things that we're able to do with these. So there's been a whole suite of different missions. This is just a graphic from NASA showing how the field has sort of moved from ground-based observatories down there in the bottom left up through space-based facilities like Hubble, Spitzer, and now the Kepler mission that we're using to find these planets and now to characterize them as well. And so the latest of these to come along is really the Kepler mission. And so I'm not going to spend too much time on Kepler because I think people here, if you're frequent visitors, you've heard a lot about the Kepler mission. So in brief, Kepler, this is a picture of the spacecraft, which is still up there orbiting around the sun, receding from the Earth. This rectangle here is the sort of a subset of the entire sky, most of the sky. And that little pink spot right there, that's the area on the sky that the Kepler spacecraft stared at for about 4 years, essentially continuously staring at about 150,000 stars in that little patch of sky. And every 30 minutes made a measurement of how bright all of those stars were, sent the data back to Earth, and all the folks just across the road over at NASA Ames poured over all those data looking for those transit signals that I was just telling you about. And so it's the Kepler mission was really a very deep, narrow, focused survey driven by a particular science goal, namely measuring how frequently do Earth-like planets occur around Earth-like stars when the planets are on Earth-like orbits. And so that's another talk entirely. But so Kepler ran for about 4 years, was very successful. Unfortunately, so a spacecraft like Kepler, to point precisely at this field, requires a component in the spacecraft called what are called reaction wheels that just control how accurately you're pointing along each of the 3 independent axes of space. So you need at least 3 wheels to point precisely. Kepler went up with 4, so it had a spare. Unfortunately, after about 4 years, not just 1 but 2 of these wheels actually had malfunctioned and had stopped working. So the spacecraft wasn't able to point precisely anywhere on the sky. And so it seemed possible that the mission might just be entirely at an end, because it couldn't, if you can't point stably, you can't measure precisely enough the brightness of these stars. Luckily, some very clever engineers discovered a way to point the spacecraft stably just using 2 reaction wheels. And this diagram sort of shows it here. The main idea is that you still have 2 wheels to control 2 axes, but there's these set of solar panels on the telescope, and if you orient the telescope in the ecliptic plane, so the plane in which all of the planets orbit the sun, you can actually balance solar pressure off of these solar panels, so that if you point a little bit off to one side, the unbalanced pressure points you back the other way, and vice versa. And so you can actually, using solar pressure, you can control the 3rd axis of rotation and point stably at a given patch of sky along the ecliptic plane. And so, but the problem is, because you're always orbiting the sun, you can only look at that patch of sky for about 3 months, or typically it's about 80 days actually, because after that you actually start pointing too close to the sun itself, and you don't want to point your big space telescope at the sun. That does very bad things to it. So that means that K2 has embarked now on a new survey of the sky, covering all of these patches along what we call the ecliptic plane. So the original Kepler field is up here, and the size of that field is just dictated by the number of CCD detectors in the camera of K2. So we can cover the same patch of sky for 80 days each, all along the ecliptic plane. And the numbers here just indicate the number of the field. It's been observing them in that order. And so now we just recently got the data down for field 12, which is over here. And so we expect to get data at least through field 16 and maybe a few fields after that. So the difference here, of course, is that whereas Kepler looked at this patch of sky for 4 years, so even if a planet had an orbital period of 1 year, you might expect to see several transits. And so you might have a pretty good handle on its orbital period and whether it was really a planet or not. K2 looks at each of these fields for only 80 days. So we're seeing a bigger portion of the sky, but for a smaller amount of time over each field. So that has advantages and disadvantages. The advantage is if there are really rare things, we're more likely to see them because we're covering 16 times as much sky. The downside is if we're looking for longer period planets, or especially if you're hoping to find planets that are real Earth analogs, you're out of luck with K2. You're going to have to go and find another way. But still, K2 is this mission that we're using, that I and my team are trying to use to continue the original Kepler mission's goal of finding large numbers of interesting new planets for future study. So it's sort of in a nutshell, what we're trying to do here is turn big lists of stars, essentially lists of all of the stars that K2 observes in each of its campaigns, and we're trying to funnel those down and figure out which of those actually host confirmed planets that we're reliably sure are really there and are not just some sort of non-planetary signal that masquerading as a planet, which I'll talk about in a little bit. In principle, this is, of course, not the work of a single person. This is one photo of a subset of our team. There are actually a lot of people who have joined the team in the meantime who aren't even shown here. Several of these people have actually passed through the Bay Area and or NASA Ames. So it's a group of effort from a large number of people. I'm just here presenting the results from all of us to you. So the bad news, the trouble with trying to do this, and ground-based transit surveys encountered this problem, and the original Kepler mission ran into it to some extent, and K2 does as well, is that there are lots of different astrophysical scenarios shown here, each of which can sort of masquerade as a planetary transit. If you have a dark planet with its shadow crossing in front of the star, in principle, it can be tough to distinguish that from a small planet transiting in front of the star, or a stellar eclipsing binary blended with the light from a brighter star that's closer to Earth, or even from a eclipsing binary with almost equal sizes where just they're sort of grazing. They only block out a little bit of the light. In principle, with only the photometry, the measurements of brightness that we get from K2, we're not always able to tell which of these scenarios we've observed when we see that U-shaped transit dip. So that's the bad news. The good news is that that means we get to go out to lots of observatories across the world and travel to exciting places and collect ancillary data to confirm or rule out these different planets. So this is a picture of me and my student Arturo Martinez. We've got to go down to Chile for several week-long observing runs up in the Andes Mountains. And so he took some near-infrared spectroscopy of some late-type stars to improve our knowledge of their stellar parameters and confirm whether they were hosting planets or not. We also get optical spectroscopy at much higher spectral resolution from facilities like the Automated Planet Finder that I mentioned right up here at Lick, and also from telescopes out at Keck in Hawaii. So we get to go to both local and exotic locations there. We get not just high-resolution spectroscopy, but we get very high-acuity imaging from techniques like adaptive optics imaging, which, even though we're on the ground looking through the Earth's blurry atmosphere, essentially allow us to get diffraction-limited images, essentially images quality comparable to what you could get in space, to look very closely for, there's a picture of Erica Gonzalez, my student who's working on this, to look for other point sources that might indicate that there were multiple stars all in the big aperture that K2 was using to measure the stellar brightness. And so this is one of the few surveys where we're doing this sort of high acuity imaging where we're hoping to see no other little point sources. Some people do these sort of surveys looking for other points, hoping that they are planets. We're just hoping not to see any other stars, because if we don't, it's probably not a stellar binary. So we take all of these data and all of these measurements, and all we have to do is put them into this simple flowchart and follow them from the top up to down to the bottom. And so once we've done this, we can figure out whether a planet is validated and confirmed, and that makes us happy. We feel confused and upset if we turn out it was one of those false positive situations. And in some cases, we're just not able to actually determine whether the planet is really a planet or not, so it just remains a candidate. So you just have to follow that simple plan. So there's a lot that goes into that, and you should feel free to ask me questions about it afterward. I don't want to dwell on it now. The result of all this, though, after we flow down here to these three guys here at the bottom, is that in the first 2 years of K2, we found about 200 confirmed planets that we're really sure about are really planetary and not any of those false positives. And we have, between us and other teams out there, there are probably 3 or 4 times that number of candidates that are still out there, or things that have been deemed false positives. So about 100 planets per year, which is, if you are familiar with the Kepler mission, is a much lower yield than the original Kepler mission was able to produce. And I think that's really a testament to the original design of the Kepler mission, when it's able to, using all of those reaction wheels, point stably at the same patch of sky for a long time, which is a much more stable platform for this sort of science than K2 was. But luckily, we're still getting something pretty productive out of K2. So what's shown here on this plot, each of these gray points, so this is a measure of how bright a planet's star is. We like stars that are brighter because it's easier to measure their transits later on. It's easier to measure their radial velocities and measure the planet masses. It's easier to study the planet's atmosphere. So we like planets around bright stars. We also like smaller planets because, I don't know, these days everyone is getting more and more excited about small planets. It has something to do with this 1.0 Earth radii, I think. So what we really want is to find large numbers of small planets orbiting bright stars. Each of these gray points are planets that were known before the K2 mission really got going. And so most of these were actually produced by the Kepler mission, the original Kepler mission. And so you can see there are thousands of points there. They just all blend together. And there's a lot of them. And there's not nearly as many as of our K2 systems, which are shown here, color-coded by the temperature of the star there. Even though I made our symbols much bigger than the Kepler planet symbols, there still aren't as many, obviously. But what's exciting to us is that there are much larger numbers of these planets around brighter stars. The sort of typical stellar magnitude for our sample is maybe 2 or 3 magnitudes, so about a factor of 10 brighter than the stars found by the Kepler mission. And that's entirely a product of the fact that we're surveying a larger fraction of the sky for a shorter period of time. So what that means is, if we sort of bin this up and quantify it, it means that for sort of planets around brighter stars, it's sort of anything smaller than Jupiter, we're increasing the number of planets known, small planets known to orbit bright stars by something like a factor of 50%. And this is after the first 2 years. We expect K2 to last another 2 years beyond this. So that means that by the end of the K2 mission, we should have effectively doubled the number of small planets known to orbit these bright stars. And again, that means that we'll have now twice as many planets to measure interesting transits on, measure radial velocities and planet masses, study planet atmospheres. So when we made this plot and actually found this result, we're really excited. This is real vindication to us of our whole K2 effort, because our whole goal was really exactly this, finding lots of planets orbiting bright stars. And so we're really accomplishing that. So in principle, each of these points here could be a little story in itself. We don't have that much time, so I'll just walk you through 3 mini case studies just to talk to you about some of the examples. And you don't have to remember these numbers either. Astronomers give all sorts of weird names to the stars and planets that they look at. These are 3 examples of that. So the first of these is K23, and K23 BCD. B, C, and D are the names of 3 planets orbiting the star called K23. And it's called K2 because it was a planetary system discovered by K2. The 3 means that it was the 3rd planetary system that K2 identified and confirmed. But the 3 is also sort of fun because there are 3 planets orbiting this system. So this was one we identified about a year and a half, maybe 2 years ago now. And it was the first multi-planet system discovered by K2. And it was the first system found of planets that K2 found orbiting a small, low-mass, cool star, an M dwarf, we call it. And what you can see here at the top, this top panel, each of these dots is one of those 30-minute measurements of the brightness of the star, called K23. And you can see that it extends, these are not years, these are days. They extend about 75, 80 days, so the full length of one K2 campaign. And each of these little dips, which I've marked here with a color-coded line, is one transit of one of those different planets. And if you look at that plot, you can convince yourself that the different colors occur periodically on 3 different periods. And if I fold them on orbital periods of about 10 days, about 20 days, and about 45 days, you can see that there are indeed 3 coherent transit signals here in this system. And this system was we thought it was pretty fun for a couple of reasons. First, the sizes of the planets are all pretty small. So the innermost planet is the biggest at about 2 times the size of the Earth, and the outermost one is only about 50% bigger than the size of the Earth. And what we know from studying other planetary systems is that 1.5 times the size of the Earth is about the point where we expect planets to be dominated by rock rather than just be sort of miniature gas giants. So we think at least this K23d could be a rocky terrestrial world, even if the the inner 2 planets are maybe gas giants. And it's interesting too that we think in our solar system, I think we're used to thinking of the small planets are on the inside. As you go farther out, the planets get bigger. K23 is obviously an example of the opposite. The innermost planet is the largest, and as you go out, the planets get smaller rather than bigger. Also interesting to us, if we look at the amount of flux incident from the host star onto these planets relative to the amount of flux incident on the Earth in an averaged sense. While the innermost planet is pretty hot, 10 times more irradiated than the Earth, the outermost planet, there's a big uncertainty here, but in principle, it could be a level of irradiation comparable to that received by the Earth. So that was kind of fun too, because it was a planet that could be rocky, could have comparable surface temperatures to the Earth. Of course, it could also have comparable surface temperatures to the Moon, which would be much less hospitable than the Earth. So this isn't a planet that we can say has an atmosphere or not, but it's actually something we're already looking at now with the Hubble Space Telescope to try and start learning something about whether it has an atmosphere, and if it does, what might it be made of. And this K magnitude here is just remember, magnitudes are how astronomers measure brightness, I mentioned, and 8.6 just means pretty bright. So we were happy about that. So another one of these that we identified just last year is a system now called HD 3167. And so this one we only identified 2 planets that you can see here in these plots. One of them was a very long period planet with an orbital period of about 30 days and about 3 times the size of the Earth, so almost certainly a gas giant, a little smaller than Uranus or Neptune. And there's this other little thing that's marked with red that you can hardly even see in the upper plot. But when you fold it on a period of about 0.96 days, so something like 23.5 hours, you see this coherent transit signal. That means that this little planet is whizzing around its host star every 23 hours. So every day you age by a year on this planet. So not a happy place, maybe. Also really hot because it's so close to the star. And its size is 1.7 times the size of the Earth, so sort of right on that borderline of where it could be rocky or it could be a little gas giant, so we don't know. And this star is even brighter. Astronomers do everything backwards. We're very perverse that way, so a smaller number means a brighter star. So this meant it was a great target for radial velocity measurements. So we went out with each of these color-coded points are measurements we made from the high-res spectrograph in Hawaii, the APF spectrograph right up on Mount Hamilton, and the HARPS North spectrograph. And each of these points is shown here, measured over about half a year. This blue curve here is the model that we ended up converging on to fit all of these data in an optimal sense. And so the residuals here are more or less flat. And so this is a paper led by Jesse Christensen that's been submitted recently. And what took us quite a bit of time to identify these planets and figure out their radial velocity signals and their masses. But in the end, we're able to get a very clear measurement of the mass of planet B. You can see its periodic Doppler shift, phase-folded on its orbital period here. You can see planet C, the 30-day period planet as well. And what took us so long in the end was that there's actually a planet D, a non-transiting planet with a period of about 8.5 days that we didn't know about and could never have known about from the K2 photometry. And so that added a lot of complexity to the analysis. In addition, if you know anything about signal processing, you can imagine that looking for a signal with a period of about 1 day, when you're sampling it about once every night, is a very challenging aliasing problem. So we need a lot of data from multiple facilities to really zero in on these planet Doppler shifts. The result of this, though, is that we can plop these two planets down on one of these mass radius diagrams. And so planet B, right here, the innermost one, is right on that curve with the Earth and Venus of a rock-iron composition. So indeed, as you'd expect for something that's being totally blasted by this star and of this size, is probably a rock-iron planet, albeit one with a surface temperature of something like 2,000 degrees Kelvin. Planet C, on the other hand, sits up here comfortably above all of these sort of denser material composition lines, confirming what we suspected, that it must be a miniature gas giant with at least a thin veneer, if not a thicker one, of hydrogen and helium. And so these planets also, at least the outermost one, we're also planning to target with the Hubble Space Telescope and with the James Webb Telescope coming up in the next years. The final system I'll talk to you about is this is just another plot like the ones I've showed you of transit photometry. So these are days on the horizontal axis, and this is the stellar brightness. This photometry is actually from the Spitzer Space Telescope, but K2 has also observed this system. And so each of these color-coded diamonds here now indicates an individual planet. And there's actually, turns out, 7 planets that were found here. 3 were known before. And this is the system you might have heard about a few weeks ago called TRAPPIST-1. And so this is an artist's conception here of each of these little 7 planets. Obviously, the planets are bigger in this image than they actually would be. They don't almost run into each other in real life. So 3 of these were discovered originally. The Spitzer Space Telescope found 4 more of them. And then K2, just a week or 2 ago, downloaded its data, and papers were published within just a few days showing that all of these planets were indeed confirmed by the K2 mission, and the 7th planet, they were able to get multiple transits and confirm its orbit. So this is a system not discovered by K2, but such an exciting one that has generated a lot of interest. Part of the reason is that all 7 of these planets range from, I think, half the size of the Earth to something like 1.5 times the size of the Earth. So presumably, all of them are more or less rocky and Earth-like in terms of their bulk composition. Also, as you can see in this, maybe you can see in this sort of artist's conception, although there's these ice crystals because the outer planet is cold, and there's steam because the inner planet is hot, there's just liquid puddles lying around here because maybe 1 or 2 or maybe 3 of these planets lie in what astronomers call the habitable zone, where if it has surface water and if it has an atmosphere, neither of which we know, the water on the surface could indeed be liquid. So it's one of the best places we've found to date where we could hope to characterize the atmosphere of the planets and where the planets lie in a very interesting, maybe Earth-like region of irradiation and other properties. But it's going to take a lot of extra effort to confirm that. This is just a second plot on the TRAPPIST-1 system showing the things actually to scale. So this is the sun, which does not fit on this screen. This is why we have to tear the building down, because we need a bigger screen to fit the sun. TRAPPIST-1 is this tiny little red dwarf. It's almost not even a star. It's so low mass and so small. And it's basically the size of Jupiter. These things are all on the same scale here. So it's really remarkable just how small this star is. And so these are all of the planets in the system here to scale. And you can see they're bigger than Jupiter's moons, but they're really comparable in size to Venus and Earth. So this is an exciting system. I wasn't involved, I should say, in any of the TRAPPIST-1 work. I just wish I were. And I think it's one of the more exciting systems that's come around. So you all deserve to hear about it. So that's just 3 examples of systems that K2 has discovered recently and that or with follow-up observations that we've worked on characterizing. One of the goals that I'm really interested in answering with K2 also, something we're just getting started on, is to not just find individual planets, which some people sort of accuse us of just stamp collecting. We're just finding interesting individual systems with no coherent story. So one of the big coherent stories that our team is trying to answer is this one, to answer the question, how common are these small planets, especially the ones orbiting these small, cool, low-mass stars? So we know from the original Kepler mission, this is just a plot by Andrew Howard, but there have been probably dozens of people that have led papers on this same topic, that big, hot planets, this is radius and period again, short period planets that are big, like hot Jupiters, are very rare, and that planets on longer orbital periods, maybe the size of the Earth to the size of Neptune, are much more common. So I drew a little Earth here. There's a question mark because I think we're still waiting for the final results in the next few months from Kepler as to whether Earth analogs are common or not. But in general, we know around sun-like stars, which is what Kepler focused on, that small, longer period planets are more common than big, short period planets. What we'd like, the trouble is Kepler did some good work on this for these small, low-mass stars as well, but Kepler's main mission was really to answer these sort of questions for sun-like stars. So if you look at this is now the effective temperature, the temperature of the stars that both Kepler and that K2 looked at. You can see Kepler is the dashed line and K2 is the solid line. So the sun's temperature is about here. And so you can see that the Kepler mission by far targeted mainly sun-like stars because it was driven primarily by this overarching science mission of measuring planet occurrence around stars like the sun. K2 is much more community-driven. So actually all of us in the exoplanet community send in proposals to NASA saying, I would like to observe this star or that star for this science case or to answer that question. And by the process of peer review, stars are selected. And what you can see here is that although there's still a lot of sun-like stars targeted by K2, there's also this huge peak in cooler, we call later type stars, what we call M and K dwarfs. These are stars that are much cooler, much smaller than the sun. And it's something that Kepler didn't look at a lot of them, and that's mainly a fraction of just looking at this single patch of sky. Just by virtue of looking at 16 times bigger area on the sky, K2 is able to look at many more of these small, low-mass stars. And so something we're working on doing now is measuring the occurrence rate of planets around these using the much bigger sample of these stars from K2. So the way we're doing this is actually kind of fun. We're getting in, is anyone here familiar with the Zooniverse website? Few people? Okay. So Zooniverse is a site that does citizen science. It just, as far as I can tell, it tricks the innocent public into doing our science work for us. But that works out for us. And so we were actually putting together a project website on the Zooniverse site, which will use our data from the K2 mission to identify new interesting planet candidates. And not only will we identify these new interesting planets, but by injecting simulated planet signals of known period and known depth, we're also going to be able to measure our survey completeness. How well are we able to either find or how often do we miss planets of different types? And so then we're going to be able to convert our catalogs of known discovered planets into occurrence rates of different types of planets orbiting these low-mass stars. So if you want, you're welcome to check this out. We're just finishing ramping this up, and it's going to go fully live in about a week. The way it works is it just takes you to little diagrams that may or may not show things that look like transits, and you choose which of these situations you think it is. Unsure is always a good bet. So we're excited about what this citizen science is going to do, both in terms of engaging the public in the interest in our science, and also in terms of what we're going to be able to find out about planet occurrence from K2. So I talked a lot about a number of these, how we're using ground-based facilities. I only briefly alluded to, in the interest of time, how we're using Hubble and Spitzer to start to study the atmospheres of these things. And we're, of course, finding all of these planets using Kepler and now K2. The next big mission coming along is the TESS mission. And TESS, as I said, is the all-sky survey of transiting exoplanets, which is launching early next year. So whereas K2 is running right now, and it builds on the legacy of the original Kepler mission, TESS is going to be what's coming next. So there's sort of this logical progression. And it kind of works out well because both in terms of sky coverage, we sort of transition gradually from Kepler, small patch of sky, to K2, bigger region, to TESS, almost all of the sky. So TESS will cover almost all of it. But it also transitions very nicely in terms of the temporal coverage. How long of a time baseline do we have on each of these stars? For Kepler, it was 4 years. For K2, it's about 80 days. For most of TESS's targets, it'll only be about 30 days, so it'll be even shorter. But you notice I made TESS's solar panels go up here a bit above K2, because actually for a small patch of sky, TESS will actually observe for almost a full year. So it's going to be a wide range. And TESS will do this by, here's a little diagram of the spacecraft. It will tile these rectangular zones for about 30 days each. And as it rotates around the sky during the course of a full year, you can see that for most of the sky, it'll only cover it for about 27 days, this blue cover. But as you get closer and closer to the ecliptic pole, the coverage will increase because, especially up near the pole, it'll be observed essentially continuously by TESS. So you'll get almost a full year of coverage. And then TESS will flip around and do the opposite hemisphere in the sky. So a 2-year mission, it will tessellate almost the entire sky. And this little circle here is what's called the James Webb Continuous Viewing Zone. That's where the James Webb Space Telescope will be able to continuously observe any of the most interesting planets that TESS finds. So we're very excited about TESS. To just show an example, I showed this diagram earlier of our K2 planets compared to what planets had been found before, and showed you how we'd found lots of new planets that are even brighter. And if we plot what the TESS mission projects as their yield by the end of the full TESS mission, you can see these little blue stars. There are even more of them, and they're around even brighter stars than what we're finding with K2. So it's really exciting that TESS is just going to build on everything we're doing with K2 and really extend this in even more exciting directions. So I think we're doing all this. TESS is coming along right now. I'll just briefly mention that the James Webb Space Telescope, which I alluded to before, is also coming along very soon. And it uses a technique we call transmission spectroscopy by measuring the transit depth of a planet at different wavelengths of light. So if you measure a transit depth at one wavelength and then at another wavelength, if the planet has an atmosphere, the depths may actually be different. And so something like Hubble or James Webb can use transit observations to tell us exactly what the atmospheric makeup of a planet is. And so this is just an example spectrum of a transiting object with an atmosphere. So you can see signatures from methane and carbon monoxide and other features. And so targets like our HD 3167 that I talked to you about, this is just a simulation that I ran for a particular assumption about what the atmosphere could be made of this planet whose mass we've recently measured. And with just 1 or 2 transit observations with James Webb, we'll be able to get a pretty precise measurement of what the planet's atmospheric makeup is. You can see that these simulated measurements here with their error bars would track pretty well with this model, and we'd be able to back out what the planet's atmosphere is made of. So James Webb, we're using Hubble right now to do this. James Webb launches in the sort of middle end of next year, and then its observations start. The trouble with James Webb, and then TESS comes along as well to deliver really great targets. The trouble, such as it is that the proposals to use James Webb in its first year or 2 of operations are actually due less than a year from now, which stresses me out every time I think about it. And they are definitely due much earlier than the TESS mission even gets on Sky. So it's really great that we have the K2 mission operating now that's delivering the best planets we can possibly find today, so we don't have to waste any time waiting around for TESS. So that's one of the big goals we've had with K2, and it's working out very, very effectively, we think. So in summary, K2, despite I think the reports of Kepler's death were greatly exaggerated. K2 is still operating very successfully, and we're getting a lot of exciting science out of it. We have to collect lots of additional data and observations, as I mentioned, but that's a plus, I think, not a minus. And we're finding large numbers of new interesting planets. Some of these will be good for atmospheric studies, for measuring the masses or bulk compositions, measuring dynamical interactions of all of these different planets. As we saw with TRAPPIST-1, maybe even finding planets that could be in the habitable zones of these stars, where someday we could hope to search for signs of life. And so there's lots of exciting work that lies ahead in that direction. It's been great to share this work with all of you. So thank you.
All right, that was really great. We have some time for questions. I'll go around the room as I see them.
Thank you. That was a great talk. And I think per reaction wheel, K2 is doing really well. I'd like to very briefly thank Adrian Brown and the SETI Institute for running this series as long as you have. It's been awesome. My question is about the observation of the TRAPPIST-1 system. I observed for about 80 days, and I was wondering if you were able to rule out an 8th planet.
So as I said, I wasn't involved in the TRAPPIST work, so I can't comment in detail. All I know is there have been no announcements of an 8th planet. So that either means nothing or they're biding their time for a big press release.
I take it your method depends upon the fact that the planets you detect are orbiting in a plane which you see edge on from here.
That's right.
How is the distribution of those planes? Is there reason to suppose that many of them are in that plane, or are they random, or what?
That's a great question. So that's not something I've worked on particularly, but there's been a lot of work done in that area. I think the fact that we see so many of these multi-planet systems, for example, TRAPPIST, where there are 7 planets, all that we see transit, really gives us very strong reason to believe that a lot of these extrasolar systems orbit in a very, very flat plane, maybe comparable in flatness to that of our own solar system. But there's also certainly been work done claiming that there's at least a subset of these systems where the planes of the planets could be substantially misaligned. And that could occur because early in the planet formation history, the planets approach too close to each other and gravitationally perturb each other. They can, in principle, scatter all over the place, so things can get messy.
I had a question about that non-transiting planet around HD 3167. Yep. What kind of hypotheses were tested? Just single planet perturbations or multiple planet perturbations to come up to that conclusion?
So the conclusion that there was an additional radial velocity signal was pretty robust. We weren't sure at first because the 2-planet model, we knew about the 2 transiting planets, definitely didn't fit. And so we tried models with a 3rd planet, with a 4th planet. We didn't need 4 signals. We did need 3. It could still have been things like rotating star spots with a stellar rotation period of 8.5 days. But for other reasons, that doesn't seem to be very likely. So we're pretty convinced that this is an intermediate planet that's just happened to not be transiting.
I was wondering what kind of pointing accuracy you get when you don't have the 3rd reaction wheel. Is it just as, I understand you're using radiation pressure for one axis. Is your RMS pointing error about the same as with 3, or is it better or worse?
So with K2, the pointing is definitely worse than it was with Kepler. And so that's, I think, our single biggest challenge in dealing with the data. Someone in the audience probably knows better than I what the original Kepler mission's pointing accuracy was. 0.01 arc seconds. So that's very small. That's something like 1/40th of a pixel on these detectors. So with K2, the pointing, because we're sort of rolling around the axis, near the center of the field of view, the pointing accuracy is pretty small, but near the edges, it can be many arc seconds, many pixels even, so maybe as many as 10 arc seconds. So substantially worse. I think as much as anything, that's the reason that Kepler saw thousands of planets and we're seeing hundreds.
Ian, that was a very nice talk. Thank you. I have two questions for you. One is, if we assume that the stars around the Earth are homogeneously distributed, why you think that TESS will bring us different demographics than K2? Because basically, what is the difference between observing this patch of sky than all over the sky if we have numbers that are 200, 300 planets should be the same? Is there any reason why you think that those results will be game changer or different than what K2 has done?
I don't think that TESS will deliver especially new results in that sense in terms of planet occurrence rates, for the reasons you say. I think K2 will definitely do different things than TESS did, because remember, Kepler just looked at this single little patch and it targeted a very specific subset of stars. With K2, as I mentioned, that we're looking at many more late-type stars. K2 is also observing a number of young clusters where there are very young stars that might have planets still in the process of forming or only recently formed. So that's something new with K2. TESS will look at some of these, but TESS will look at stars that are even brighter, and so there'll be, I don't think it'll reach a lot of these young clusters, or not so many maybe of the cooler low mass stars. So that remains to be seen. So for example, a system like TRAPPIST-1, which is only, pretty close, is only 40 light years away from the solar system, would be way too faint for TESS, because the telescope on TESS is just much smaller than it is on K2.
Thank you.
But in terms of finding bright things under nearby bright streetlights, TESS will be great.
You mentioned something about these planetary systems are very different from ours. Could you say a little bit about the differences from ours?
Sure. I think the single biggest difference that came to my mind when I had that plot up there is that in our solar system, Mercury is the closest planet to the sun, and its orbital period, its year, is 88 days. 88 days is about the length of one K2 campaign. So if all solar systems were like the Earth, at most we might occasionally see a transit of a Mercury, which might be too small for us to detect anyways, and not much else. But instead we find hundreds of planets, all with orbital periods much smaller than that of Mercury, and really all of the things we're finding, because it's what we can see, is all much bigger than Mercury, most of them bigger than the Earth. So many solar systems out there have large numbers of planets bigger than the rocky ones in our own solar system, way closer into their host stars than anything in ours. That's the single biggest thing that always strikes me. Does that mean something? I think it's it certainly tells us a lot about planet formation, and that although there's been a lot of work over the years trying to sort of from Immanuel Kant in the 18th century onwards, trying to explain how our solar system and how the planets formed and how it came to be as it is. It turns out there's a lot, you can explain a lot, but there's a lot of fine-tuning involved. And so I think the results from the Kepler mission in terms of how frequently these planets occur on all these different orbital periods was more or less completely unpredicted by everyone trying to predict how planets form in a general sense. So it's been a big surprise.
Thanks, Ian. Yeah, my question was along similar lines in terms of the fact that we were surprised by these very short orbital periods, and particularly these large planets. Does it correlate at all to the age of the star, or what are we learning, or what are we theorizing about these large planets with very, very short orbital periods? What does that correlate to, if anything, and what does it tell us about planet formation?
Well, when we're talking about the very large planets, I think it tells us that they couldn't have formed there initially, because based on what we know about disks of gas and dust where planets form around other young stars, there's probably just not enough material that close into the star to form something the size of Jupiter, say. So these things must have formed farther out and somehow found their ways much closer into the star where we see them today. So it tells us something about how planets migrate and how planets form. I don't know that we see big correlations in terms of age, just because it's really tough for lots of reasons, whether it's radial velocities or transits, to look for planets around young stars, planets of these sizes anyway. So I don't know about young stars. We know, for example, that giant planets occur more commonly around stars that have more heavy elements, more metals in their atmosphere, in their bulk composition. I don't think it's clear whether that's the case for planets the size of the Earth or not, but people are still looking.
Thank you for a wonderful talk in terms of, in particular, the emphasis on K2 and its differences. One of the things K2 does that Kepler did not do was emphasize the small stars that you're talking about. One of the things we'd really like to know are the frequencies of planets around stars. For Kepler and the stars like the Sun, that number is something like 1. On average, every star has a planet.
Yep.
Do you have some feeling for how that number varies for the M dwarf? Are you finding more or less?
We don't know yet. We're still ramping up on our efforts on that front, but answering that question is exactly what we want to do. I think just for the benefit of other folks, previous studies using the M dwarfs that Kepler did look at suggested that these lower mass stars have larger numbers of small planets than do stars like the Sun. And that's something else we just want to test and confirm with K2 and or see how that varies in different galactic environments, not just in the single Kepler field.
Hi, on your the very first plot you showed of planet size versus radius, there was a gap at about Neptune size, which is that real or is that a selection effect of some sort?
Talking about
Yeah.
this plot.
Yeah, there's a sparse region.
Right up in here?
Yeah.
Yeah, so that gap is real. Well, it's real to some extent. So there are a lot of selection effects going on in this plot. That is to say, this is planets discovered not just by Kepler, but by Kepler, by ground-based surveys, transits, and radial velocities. So the reason there's a huge pileup of hot Jupiters is not because they're intrinsically common, but actually just because they're so darned easy to find. So I think the better plot is the one I briefly popped up, this one here. So here, this is the same plot, though it's only looking at a subset of orbitable period. Each of these white dots is one planet or planet candidate that was identified early in the Kepler mission. But the color coding, where red is rare and blue is common, comes from accounting for all of those completeness effects, sort of backing that out. So if I were to look here, we don't see many planets in this regime, but I think it'd be tough to say that there's a gap once we account for those sort of effects. So I'll retract my earlier answer and say not a big gap.
I'll ask my own question. On that particular plot, am I reading the top together right to say that that is only for sunlight stars, which means that you don't have to correct for stellar flux? Or because if you're going to include the M dwarfs, then you might want to do a similar plot where the x-axis is flux and not orbital period, right?
That's right. So this particular survey focused mainly on sun-like stars. So there, and as I said, there have been other surveys using Kepler data for late-type stars as well.
If you were to choose a star system some distance away, 40 light years or whatever, and someone there had the same technology that you're talking about today, what would they see if they looked toward our sun?
It's a good question. So I think you're sort of asking what sort of transits would our solar system planets create? Yeah. So for example, for a star the size of the sun with a planet the size of the Earth, so we can sort of put them up for scale here. Remember, the sun is off the edge of the plot, and the Earth is this little blue dot. And so the transit depth from an Earth-like planet around the sun is something like 1 in 10,000, so 10 to the minus 4. So that's pretty shallow. That's a pretty small effect. But the Kepler mission, and K2 to a lesser extent, found large numbers of planets with transits that are that deep or even shallower. So it's not impossible. On that same question, one of the fun things about K2 is that K2 is only surveying the ecliptic plane, and it finds these multi-planet systems, all of which must be presumably orbiting more or less in a plane. Well, that means if a planet in that solar system were surveying their ecliptic plane, they would also see our ecliptic plane. It's like K2 is looking at the systems that could be looking back at us in the same way. It's fun.
Yeah. there's been some uncertainty over the mass, luminosity, and radius relationship of M stars. And K2's picking up a number of M stars that are close enough that we have good distances to them. And of course, the size of the star has a lot to do with what you think the size of the planets going around them are. So how are we doing on M stars and getting those air bounds smaller?
So the question here is relating to the fact that we only understand these planets that we discover, essentially, we only understand them as well as we understand the stars they're orbiting around. And M dwarfs, these low mass stars, these low red stars in particular, are notoriously difficult to do that. For stars like the sun, it's pretty easy. I think getting, say, a size or a mass for one of these stars at the 20% level is pretty easy these days. At the 10% level, we can do it pretty well. Doing it better than that becomes really tricky. That'd be my short answer. The Gaia mission, which is going to release its data for all of these stars and give us ultra-precise distances for all of them in the next year or two, I think is going to go a long way toward helping with that.
To back up a question, if they were looking at us with the Earth transiting our sun, it wouldn't be just the Earth, it would be the Earth-Moon system.
That's right.
So is there anything in the data that suggests exomoons out there?
That's a good question. So in principle, you're right. If a planet has a moon, right? If you saw the transit of Jupiter, and then there was also a transit of Ganymede, or not, there's a little bit difference. So people have looked through the Kepler data these many years, trying to find hints of what they call exomoons. So far, no convincing detections. That's mainly just because it's tough. It's tough but doable with Kepler to find planets the size of the Earth. Real tough to find smaller planets. And that's only if the planet is occurring periodically. If it's a moon orbiting a planet, the signal is only sort of quasi-periodic, and it's maybe masked by the bigger signal of the planet it's orbiting around. And maybe there aren't moons the size of the Earth, in which case maybe Kepler didn't quite have the sensitivity to do that. But people are still looking, and they'll look with K2 and they'll look with TESS. So.
Okay, my question has to do with the flare activity of M stars. That seems to make habitable zones more uncertain. And I'm wondering if slightly warmer stars, K stars, have less flare activity and might be more precisely, you can define the habitable zones more confidently around them.
Sure. So I broke one of my own self-imposed rules in this talk, which was that I actually said the words habitable zone. Usually I try not to do that because it even to people who know much more about it than me, it means different things to different people. Different atmospheric modeling groups have their own definitions of the habitable zone that aren't quite the same. So I think there's a fair bit of wiggle room there. It's not an area that I work on in particular. I think the work that's been done shows that the flaring activity of a sort of moderately active M star isn't the end of the story for potentially a planet being habitable, or at least maintaining an atmosphere and liquid water. But more than that, lots of work still needs to be done.
All right, this has been a really great time. Obviously, a lot of interest from the audience. We want to present our SETI Talk mug to Ian as a token of thanks for being with us. Let's thank Ian Crossfield.
Thanks. Thank you.
A few more words from Bill?
Yeah, just again, thank you for being the last speaker here at Microsoft. By no means the last speaker.
My pleasure.
So again, and Felix, thanks again to you and the team, and thanks for hosting us all this time. We will keep you informed about our next location. We will have a talk in April, so just stay tuned for that location. And remember, there's the Ryder Cup, the Davis Cup, the Stanley Cup, and the SETI Cup. So this is a prized possession. So thank you very much. Thanks, Ian.
Thank you.
Thanks, everybody, and we'll see you again very soon.